In the last part of this lecture, we'll discuss two types of products of vectors, and they are very important in electromagnetics. Because very often in electromagnetics, we need to determine the component of a vector in the direction of another vector, or the component of a vector tangential to a plane, or the component of a vector normal to a plane. We have this very often in for electric fields and magnetic fields. So the first type of product we'll talk about is called the scalar product. It's simply you take two vectors and you do what we call the dot product. So it's denoted by A dot B as shown here. A dot B is simply the scalar product between A and B, and it has two expressions. The first one is that it is modulus A modulus B cosine theta, where theta is the smallest angle between them, between the two vectors. Remember, any two vectors will have two angles. The angle theta, which is a small angle between them, and another angle which is 360 minus theta. Of course, when we do the dot product, we imagine that the two vectors are starting from the same point. This is how you should imagine this product. So the dot product mathematically is equal to modulus A modulus B cosine theta, where modulus A is the magnitude of A, or the strength of A, modulus B magnitude of B, cosine theta is the cosine of the smallest angle between them. Now, if we select one of these two vectors to be unit vectors, then this dot product will give us, if say is A is a unit vector, then its modulus is 1. Modulus A is 1. Then A dot B will give you modulus B cosine theta as shown here. Modulus B cosine theta is nothing but the length of the projection of the vector B in the direction of the vector A. It is this length here. You can see this here, the length of the vector B is modulus B, and this angle is theta, the angle here is theta. The modulus B cosine theta is the projection of B in the direction of A. So if you want to know the component or the projection of the length, or let's be more accurate, if you want to determine the length of the projection of a vector in the direction of another vector, first get a unit vector in the direction of the second vector and then do the dot product. So this will give you the solution. So again, I'm repeating this again. If A is a unit vector, then A dot B will be equal to modulus B cosine theta. Modulus B cosine theta is simply the length of the projection of B in the direction of A. So if you want to get the length of the projection of B in the direction of A, first get a unit vector in the direction of A, and then do the dot product between A and B. And one thing to warn you about, that theta here is the smallest angle between the two vectors. And there are two angles, the smallest angle and the one which is bigger with 360 minus the smallest angle. In Cartesian coordinates, the inner product have a more similar expression, which is simply you multiply the corresponding components and you sum them. So A dot B will be equal to AX BX plus AY BY plus AZ BZ. So we have now discussed two approaches for calculating the inner product for Cartesian coordinates. Either modulus A modulus B cosine theta, or you sum the product of the two of the corresponding components. So AX BX plus AY BY plus BZ AZ. Inner product of vectors is commutative. As you can see from the expression we have here, it doesn't matter if they reverse the B component or the A component. So A dot B is equal to B dot A. It's also distributive over addition. So A dot B plus C is equal to A dot B plus A dot C. So in other words, if you sum the two vectors B plus C first, and then you get the vector sum, and then you dot product that with A, is exactly equivalent to doing first an inner product between A and B, and then doing an inner product between A and C, and then summing them. Remember, an inner product is a scalar. It's not a vector. It's a number. Okay, so an inner product converts the two vectors into a number. If we do the inner product or the dot product or the scalar, they call it all these names: dot product, inner product, scalar product between a vector and itself, as shown here in this step. So you can see here A dot A is equal to AX plus AY plus AZ. So this gives you the sum of the squares of the components, which is the modulus of the vector squared. So in order to want to get the modulus of the vector squared, you simply do an inner product between the vector and itself. Now we know inner product is equal between two vectors equal to the modulus of the first vector multiplied by the modulus of the second vector cosine theta. If the theta between the two vectors is 90 degrees, if these two vectors are orthogonal, then the dot product will give you 0 because cosine of 90 degrees is 0. So inner product is usually in some cases used as a measure of orthogonality between vectors. So if you take the dot product between ax and ay, the unit vectors in the x and y direction, this must give you 0. Ax dot az will also give you 0. Ay dot az will also give you 0. Why is that? Because all these are orthogonal unit vectors. So the angle between each one and the other is 90 degrees. On the other hand, because these are unit vectors, if you take the dot product between any one of them and itself, it will give you the modulus of that unit vector squared, which is 1. So ax dot ax is equal to 1, ay dot ay is equal to 1, az dot az is equal to 1. And this is used very often in electromagnetics in many derivations of theorems and in many applications. So you have to keep in mind that coordinate directions are normal to each other. The dot product between the unit vectors in the direction of these coordinates will give you 0. And if you take the dot product between a unit vector and itself, it will give you 1. Because by definition, the inner product is the modulus of the sum squared. We can here take a look at this example. We have two vectors, t is equal to 2ax minus 6ay plus 3az, and the vector s, which is ax plus 2ay plus az. We would like to know the scalar projection of t on s. So if we project t on s, what is the length of that projection? It's a scalar, it's a number. The vector projection of s on t, if we project s on t, what will be that new vector? It's not really the length, it's now the vector itself. And what is the smallest angle between t and s? Again, we explained this in the previous part. In order to get the scalar projection of a vector t on a vector s, what you have to do, you have first to determine the unit vector in the direction of s. And then if you do an inner product between this unit vector and t, this will give you modulus t cosine theta, which is really the projection of t, the scalar projection of t on s, or the length of the projection of t on the vector s. In order to convert the same thing, you have to do it if you want to get the projection, the scalar projection of s on t. You have first to determine the unit vector in the direction of t, and then you take the inner product between s and that unit vector. This will give you modulus s cosine theta, which is the length of that projection. Now, this length, if you want to convert it to a vector, it is going to be in the direction of the unit vector in the direction of t. The smallest angle, we can get that because we know what is the inner product between the two vectors. We know their modulus, and you know that the inner product is equal to modulus t modulus s cosine theta. Then we know what is cosine theta. So let's take a look at a more detailed explanation of this solution. So this is what's required in this example. We have here the vector t. This is t here. This is the vector s. I draw them both emanating, starting from the same point here. I call this one, it doesn't have to be the origin, but I just call it point B here. It doesn't matter. And I want the first part to obtain the projection of t on s, which is here denoted by t subscript s. This is the length. We'd like to know if we project t on s, what will be this length. The second part, we want to obtain the vector projection of s on t, which is the vector st. Notice that this vector is in the same direction of t, but its length is equal to the length of the projection of s on t. So it is actually given by this length here. Okay, again, as we explained earlier, this is all related to inner product. So the definition of inner product between t and s is modulus t modulus s cosine theta. The inner product between t and a unit vector in the direction of s will be modulus t cosine theta, which is the length we are looking for, ts. So first get the unit vector in the direction of s and then do another product. For the second part, we get a unit vector in the direction of t, and then do an inner product with s. So this will give us this length here, this length which I call it st. In order to convert it to a vector, you multiply by the inner product in the direction of t, which I will denote by at. If you want to determine the angle between two vectors, it's very simple. Get their inner product and then divide it by the modulus of the first vector multiplied by the modulus of the second vector. Because an inner product by definition is modulus t modulus s cosine theta. This will give you cosine theta, and you can proceed from that point. Now, so let's see a detailed explanation here how things will go. So the vector s is given by ax plus 2ay plus az. So the unit vector as in the direction of s is equal to s divided by its modulus. So it's equal to s divided by square root of 1 squared plus 2 squared plus 1. So it's divided is given here in the final answer, s divided by square root of 6. So it's equal to ax over square root of 6 plus 2 over square root of 6 ay plus 1 over square root of 6 az. Now, if you want to get the length of the projection of t on s, what you have to do, take the inner product between t and this unit vector. So t has three components, 2ax minus 6ay plus 3az. Do an inner product between that and the unit vector. The unit vector here is equal to 1ax plus 2ay plus az divided by the length of the vector s, which is square root of 6. And here in this step here, I did not really write them in the form ax, ay, and az. I simply put the components. It's very easy. Dot product between two vectors, you multiply 2 by 1 for the x component plus minus 6 plus 2 for the y component plus 3 multiplied by 1 for the z component. So 2 minus 12 plus 3. So this will give you here 7, I believe. So minus 12 plus 2 is minus 10 plus 3 it's 7, minus 7. Minus 7, if you divide it by square root of 6, you get minus 2.8577. What does this mean to have a negative length? The length, of course, is not negative. What is negative is the cosine of theta, because the answer that you got is equal to modulus t cosine theta. So this means that the angle between the two vectors is actually greater than 90 degrees. And actually, if you try to draw it, this is how probably things will look like. This is s, and here this is t. So the angle between them is more than 90 degrees. So if we project t on s, your answer is 2.8577. But because this angle theta, which is the smallest angle between them, it's still the smallest angle, because it's between 0 and 180. It's actually greater than 90 degrees. But it's actually between 90 and 200, and in this case, and 270. So it's this angle here will have a negative cosine, and this y explains this negative sign. So the answer, I left it there written with a negative sign, but I want you to understand where did this come from. The projection, the length is positive, but the cosine of theta is negative. So this is telling you that the angle between these two vectors is between 90 and 270 degrees here in this case. Now, if we try to get, for the second part, we want to get the vector projection of s onto t. So we first have to get the unit vector in the direction of t. And this is in this step here where I'm showing you, where you divide t by its length. T has components 2 minus 6 and 3. We divide them by square root of 4 plus 36 plus 9. Numbers cooperated here because this will give you square root of 49, which is 7. So the unit vector in the direction of t is equal to the vector t divided by 7. So it's equal to 2 over 7 in the x direction minus 6 over 7 in the y direction plus 3 over 7 in the z direction. I simply wrote it here in the more concise way, t over 7, just to save space. Now, to get the vector projection of s onto t, we first get the length of the projection, and then multiply it by the unit vector in the direction of t. This length of this projection is very simple. We multiply s by the unit vector in the direction of t. So at s dot at, as we agreed, is equal to the vector t, which is shown here, divided by its length, which is 7. So if you do this dot product, and then after you are done with that, you put it in the direction of AT, which is shown here. This is AT. So the dot product will give you 1 multiplied by 2 plus 6 minus 6 multiplied by 2 plus 1 by 3. This will give you here 7. 7 divided by 7, they cancel out. This means that the length of the projection of S on T has a value of 1, which is a very interesting result. So if you project S on the vector T, you get a length of 1. So this is why this whole quantity here between the two brackets I'm showing you now gave us a result of 1. So the projection of S on T will be actually equal to AT. It will be equal to AT. It's equal to T divided by its length. Actually, I should correct myself. There's a negative sign here. The answer is not 1. The answer is minus 1. Because it's 2 minus 12 plus 3, so it's minus 7 divided by 7, you get minus 1. So in other words, indeed the length of the projection is equal to 1, but because the angle between them is greater than 90 degrees, you have this minus sign. Okay, so the length is indeed 1, but the angle is greater than 90 degrees. You have this negative sign. So this is now the ST, the vector projection of S on T is equal to minus AT. Is minus AT. So it's a unit vector, but it's pointing in the opposite of the vector T. And of course, if you divide 2 by 7, 6 by 7, and 3 by 7, you get these decimal numbers here. In the last step, we tried to get the angle between the two vectors, and we agreed, because of the definition of the dot product, T dot S is equal to modulus T modulus S cosine theta. So this means that cosine theta, the smallest angle between any two vectors, is equal to T dot S divided by modulus T modulus S. Most of that was calculated before. We know that modulus T is equal to 7, modulus S is equal to square root of 6. We know T is equal to 2 minus 6 and 3, and S is equal to 1, 2, and 1. These are the components. So if you do the dot product, you get 2 minus 12 plus 3, so you get minus 7. Divide by 7, so the cosine theta is equal to minus 1 over square root of 6. If you do an inverse cosine of minus 1 over square root of 6, you get 1.9913 radian. In order to convert from radian to degrees, what you do, you multiply this number, which is 1.9913. You multiply it by 180 degrees, and then you divide by pi, which is 3.14. Okay, and this answer will give you 114 degrees. So indeed, the angle between the two vectors is greater than 90 degrees. This is the smallest angle between them, because the other big angle, which is going all the way around, will be 360 minus 114. So indeed, they have an angle which is greater than 90 in this case. The second type of product we talk about is called the cross product between two vectors, and this product again plays very important role in electromagnetics. Very often we would like to determine a vector which is normal to two given vectors, and this is what the cross product gives us. The cross product, or called actually the vector product sometime, gives us a vector which is normal to the plane of both vectors. So here, if you take a look at this figure here, figure A, if you have a vector A and vector B, you draw them starting from the same point. If you do A cross B will give you a vector normal to their plane, and it is pointing in the direction of progress of a right-hand screw rotating from A to B. So if you imagine the right hand, we call it the right-hand rule. If you go around from A to B, the right-hand screw will progress in the direction of A cross B, which is shown here. Now, in terms of value, what is the value of this? The value of the cross product, it is modulus A modulus B sine theta AN, where AN is the unit vector normal to the plane of the two vectors. So it's a vector. So the answer is a vector. What is its magnitude? It is modulus A modulus B sine theta. What is its direction? It's the direction of the unit vector normal to both planes. How many unit vectors we have normal to A and B? We have actually two. one is pointing in this direction and another one is pointing in this direction. Which one should we pick? Of course, we apply the right hand screw rule. When you rotate from A to B, the right hand screw will move in the direction of AN, which is going to be here in this direction. So the one shown here. So for this shown A and B is going to be this one. Okay, so the other one, the other direction here, which is minus AN, is actually the direction of B cross A. Is the direction of B cross A. So now you must understand this. What is the meaning of cross product? It gives you a vector which is normal to the plane of the two vectors in the direction of the progress of a right hand screw from the first one to the second one. What is its magnitude? Magnitude is modulus A modulus B sine theta, where theta is the smallest angle between the two vectors. And we use it very often as a measure in this here, the cross product. We use it very, very often to see the angle between the two vectors. Of course, if you have two vectors in parallel, or they are in parallel, so there's theta is 0, then sine theta is 0, then cross product will be equal to 0. So it can be used as to measure how two vectors are in parallel to one another. The geometrical meaning of the cross product is simply the area of the magnitude of the area of the parallelogram created by both vectors as shown here. So A cross B, if you take modulus A modulus B sine theta, this number, the modulus of A modulus B sine theta, if you take its modulus value, so disregard the sign, it gives you simply the area of this parallelogram created by both vectors. But of course, as a vector, it's a vector pointing to the normal to the plane of both vectors in the direction of the progress of a right hand screw rotating from the first one to the second. In Cartesian coordinates, the cross product or the vector product is obtained by this determinant. You put the unit vectors in the direction of x, y, and z in the first row, and then you put the components of the first vector in the second row, and then components of the second vector in the third row, and then you apply the expansion of determinants. And this will give you a vector with 3 components. And this is how we usually do the calculation in Cartesian coordinates. Cross product has many interesting properties. It's anti-commutative. So A cross B is equal to the negative of B cross A. And the reason for this, as I explained earlier, because the plane normal to these two vectors, the plane combining these two vectors has two normals. And they are pointing one opposite to the other, depending on the order. So if you take A cross B, the right hand screw will progress in a certain direction. If you take the cross product between B cross A, the right hand screw will progress in the opposite direction. So the order does matter. It creates a negative sign because it reverses the direction of the progress of the right hand screw. The cross product is not associative. So A cross B cross C is not equal to A cross B cross C. So in other words, if you first take the cross product between B and C as shown here, and then the result, you take its cross product with A, is different from if you take the cross product between A and B and then you cross product with C. Cross product is distributive over summation. So if you have two vectors B and C, you sum them and then you do the cross product with A. This is equivalent to doing the cross product between A and B and then you sum it to the cross product between A and C. Because the cross product have sine theta, and theta is the angle between the two vectors, the cross product between any vector and itself is 0, because any vector has a 0 angle with itself. So this means that the answer must be 0. And you should see here, notice something, that I wrote A cross A is equal to 0 as a vector. What do I mean by 0 as a vector? It has 0 in the x direction, 0 in the y direction, and 0 in the z direction. It's a vector. It's a vector of zeros. It's not a scalar. The cross product creates a vector. But the vector here in this case has all 3 components. Because the cross product give us a vector normal to the plane of the two vectors, and because the unit vectors in the direction of the coordinates are normal to one another, you will notice that in what we call a right-handed coordinate system, which is the one we use all the time, when you rotate when you take the cross product between ax and ay, the right hand screw is moving from a to y. It must be pointing the direction of z. And when you take the cross product between ay and az, the right hand screw will progress in the direction of x. And then when you take a cross product between az and ax, the right hand screw will progress in the direction of y. So this is called a right-handed coordinate system. And it's not that difficult to see. Ax cross ay will give us the unit because these both are normal. These two vectors are normal to one another. Then theta is equal to 90 degrees. Then sine theta is equal to 1. So this will give you modulus of the first one multiplied by modulus of the second one. So it gives you 1. So and it's pointing the normal direction, which is az. So ax cross ay will give you az, ay cross az will give you ax, and az cross ax gives you ay. And you should remember this cycle, this circle. Ax cross ay gives rise to az, ay cross az gives rise to ax, and az cross ax gives rise to ay. And of course, because theta is the angle between the two vectors, and the same vector will have zero angle with itself, we have ax cross ax is equal to 0 vector, ay cross ay is equal to 0, az cross az is equal to 0. And remember, I'm putting them as 0 vectors. So it's 3 zeros, 0 in the x direction, 0 in the y direction, and 0 in the z direction. Let's have an example on that. We'd like to get the dot and the cross product and the angle between the two vectors. B is equal to 2ax minus 6ay plus 5az, and q is equal to 3ay plus az. So here q does not have an x component. Its x component is equal to 0. It is only it has components in the yz plane. It is parallel to the yz plane. It's normal to the x-axis. So again, this is direct application. We know the dot product. Simply multiply the corresponding components and sum them. We know the cross product. You create the determinant and you expand it. The angle is very easy. You can obtain it from the dot product. Divide the dot product by the modulus of the first vector and the modulus of the second vector. So here in this case, the dot product is equal to 2 multiplied by 0 plus 6 minus 6 multiplied by 3 plus 5 multiplied by 1. So this will give us minus 18 plus 5 is equal to minus 13. The cross product, we create the coordinate, and here I replaced the ax, ay, and the ez by I, j, and k. This usually we do that. It doesn't matter; they are equivalent. I means unit vector in the x direction. J means unit vector in the y direction. K means unit vector in the direction. We use them. Sometimes we use them that way. It's fine. So I kept it that way. And you put the first vector here. So this is the vector b in the second row, and the vector q in the third row. And then you expand the determinant. So this here will give you minus 6 minus 15. So it's minus 21. And if you expand the other two, this will give you here 2 minus 0. So this will give you 2. And the third one is a negative sign. And the last one will give you 6 plus 0. So this will give you here 6. So the result is minus 21 ax minus 2ay plus 6 az. The angle between the two vectors again is obtained from the expression of the dot product. Dot product by definition is equal to modulus b modulus q cosine theta. Then cosine theta is equal to the dot product divided by modulus b modulus q. We obtained the dot product earlier, which was equal to minus 13, which indicates that the angle between them is greater than 90 degrees. The smallest angle between them is between 90 and 180, actually, in this case. So it's an angle where you get a negative sign. So this will be minus 13. So if you the modulus of b is not that difficult. To get the modulus of b, you sum the square of all you get the square of the sum of all components, get square root of 10. The same thing will happen with q. If you sum the square of all the components, you get square root of 65. If you expand all this, you get that cosine theta is equal to minus 0.51. Remember that cosine of 60 degrees is equal to, this is very similar to cosine 60 and so on. So if you take the inverse of that, whether you can get it in radian or degrees, depending on your calculator, you'll see that the answer is equal to 120 degrees. So 20.66. So almost you have make 120 degrees between one another. We have here one more example. We have two vectors. A is equal to alpha ax plus 3ay minus 2az, and beta b is equal to 4ax plus beta ay plus 8az. We want to determine the values of alpha and beta if a and b are parallel, and what is the relationship between alpha and beta if a and b are normal. The trick here, we know that if two vectors are parallel, then the angle between them is 0. And if the angle between them is 0, then their cross product must be equal to 0. So this will give us a direction. We create the cross product and try to set it to 0. And remember, the cross product or the vector product will have 3 components. For two vectors to be normal, their dot product must be equal to 0. So if we do the dot product, this will force a relationship between alpha and beta. And then we can use that relationship in our solution. So now let's take a look how this will go. If you do the cross product between a and b, and you set it equal to 0 vector, because these two are parallel, you put the vector a in the second row as shown here of the determinant. You put vector b in the third row of the determinant, and then you expand the determinant. This will give you 3 components. And then you equate every component to 0, because remember the right hand side has 0 vectors. So it's 0ax, 0ay, plus 0az. Get 24 plus 2 beta ax minus 8 alpha plus 8 ay plus 12 minus alpha beta az is equal to 0. For this is all equal to 0. So this is equal to 0 on the right hand side, 0 in the right hand side, and 0 as well. So each one of them is equal to 0. So if 24 plus 2 beta is equal to 0, beta is equal to minus 12. If 8 alpha plus 8 is equal to 0, then alpha is equal to minus 1, and this automatically satisfies the third part for the z component. So this means for these two vectors to be parallel, beta must be equal to minus 12 and alpha must be equal to minus 1. If beta is normal to a, then a dot b is equal to 0. Then if you do the dot product between the corresponding component, you get 4 alpha plus 3 beta minus 16 is equal to 0. So this relationship must be satisfied for them to be normal. Of course, we have infinite number of values. Every value of alpha will give a corresponding value of beta that allows these two vectors to be orthogonal.